Okay, welcome back. This is a short little lesson relating radical expressions and complex numbers. So this is two important topics with respect to, you keep seeing this word conjugate appear. So we're looking here at a product of real conjugates. I'm going to write product of real conjugates. You need to get this in your notes. Two super important topics that are going to lead us into our next discussions on factoring. So product of real conjugates produces what we call a difference of two perfect squares. Difference means subtract, and product means multiply. Now, product or multiply, if we multiply complex conjugates, this produces a sum of two perfect squares. What does sum mean? Sum means add. Now, let's look. Product of real conjugates. So I'm going to give you a quick example. If I say here, x plus 5 times x minus 5, notice we have real conjugates on the board. Real, at this point, you can think of real means there is no I, or there is no imaginary unit in the binomials. So we see x plus 5, x minus 5, there is no I. Okay, I is going to refer to complex. Now, we see conjugates because these have opposite middle signs. Also, notice, we have a product or multiplication of real conjugates. So x plus 5, x minus 5, we're going to FOIL and see what happens. So we're going to take our x, multiply by our x. X times x gives x squared. X times negative 5 is negative 5x. Take the 5, multiply by both. 5 times x is 5x. And 5 times negative 5 is negative 25. Why am I showing you this? This is going to save you a lot of time. Watch this. So what happens when we multiply conjugates? Negative 5x plus 5x gives what? 0x. So these two, we say, cancel out. The middle terms cancel. When you multiply conjugates, the middle terms cancel. We're left with x squared minus 25. This is called a difference. Remember, difference means subtract. So we see subtraction or difference of two perfect squares. 25 is the perfect square of 5, and x squared is the perfect square of x. Look at this. Is there a trick? Is there a trick we can use to make this fast? Yes, there is. Watch this. Well, I shouldn't cross that out. You don't need to cross this out. So x squared minus 25. We know that x squared minus 25 is a difference of two perfect squares. This is a square, and this is a square. Okay, x squared is the square of x, 25 is the square of 5. So there's a trick we can use. Watch this. We can take the x and say, what is the square of x? X times x gives what? X squared. And what is the square of 5? 5 times 5 gives what? 25. And what can we put between these? Well, we can put subtraction because we know that these are conjugates. A product of real conjugates produces a difference of squares. Subtraction of two perfect squares, and we're done. Why does this work? Because the center will always cancel out. Watch this. Product of complex conjugates, x plus 5i multiplied by x minus 5i. Notice, we're going to FOIL. Take x times x. We get what? X squared. X times negative 5i. We write negative 5ix. I is considered to be a constant, so we're going to put the I before the x. Now, positive 5i times both. Positive 5i times x is plus 5i times x. And 5i times negative 5 is negative 25i squared. I want you to notice, negative 5ix, positive 5ix cancel out because they are opposite, identical terms with opposite signs. So these cancel. Remember, when you multiply conjugates, the center always cancels. We're left with x squared, but the I squared is going to be, well, remember, I squared is negative 1, is going to change the negative 25 to what? Positive 25. So we end up with x squared plus 25. Now, we call this, because of addition, we call this a sum of what? Two perfect squares. This is a square, and this is a square. So what is our trick? Our trick is that we can just look at the conjugates to begin with. Since these are conjugates, or since they're identical binomials with opposite middle signs, we can just take our x and square it. X times x gives what? X squared. Take our 5 and square it. 5 times 5 is 25. And since we have an I on the end, these are complex conjugates. Since complex conjugates produce a sum or addition of two perfect squares, we say that this is x squared plus 25. Now, I'm going to show you that this works with radicals. Watch. So if I write root 2 plus 3 times root 2 minus 3, and we look at this as there is no I. So these are not complex, these are real. There is no I written. There is no imaginary or complex unit. Now, so we're going to say take the root 2, let's go ahead and FOIL it. Root 2 times root 2 is what? 2. Remember, root 2 times root 2 is 2. Root 3 times root 3 is 3. Okay? And now take the root 2 times the 3. Remember, we cannot multiply the 2 and the 3 together because the 2 is under a root, the 3 is not. So we glue this together. Positive times negative is negative. Put the 3 first. 3 root 2. And now take the positive root 3 and multiply by both. Positive 3 times root 2 is plus 3 root 2. And positive 3 times negative 3 is negative 9. Now notice, we can take the negative 3 root 2 plus 3 root 2. They cancel because when we multiply conjugates, the center cancels. Now do 2 subtract 9, we get negative 7. Is there a way that we can do this very quickly? Yes. What we can do is we can just simply say, what is the square of root 2? Or what is root 2 times itself? So root 2 times root 2, remember that a product of real conjugates produces a difference or subtraction of two perfect squares. So we take the root 2 times root 2. Root 2 times root 2 is 2. And the 3 times the 3 gives 9. And since these are real conjugates, we can put subtraction between these. 2 minus 9 gives negative 7, and we're done. It's much faster. So this trick really works. Watch this. If I write, in this case, 5 plus 2i times 5 minus 2i, we can FOIL this first to see. Remember, these are complex conjugates, opposite middle signs. We have an I on the end, so these are complex conjugates. Complex conjugates will produce a sum of two perfect squares. 5 times 5 is 25. 5 times negative 2i is negative 10i. 2i times 5 is positive 10i. And 2i times negative 2i is negative 4i squared. Now notice, negative 10i plus 10i cancel out, giving 0. The center always cancels. I squared is going to change the negative 4 to positive 4. So we end up with 25 plus 4, which is 29. Is there a way we can do this very fast without foiling? Yes. We can look at our first numbers. Our first numbers are 5 and 5. Take 5 and 5 and square it. 5 times 5 is 25. Now take the 2 and the 2, multiply them together. 2 times 2 is 4. Since there's an I on the end, or these are complex conjugates, we put addition between here. 25 plus 4 is 29. So we can get an answer very, very quickly. So now, how is this going to speed up problems that we're doing in this class? Let me show you. So you remember, with respect to radical expressions, if I write 5 over root 2 minus 7. Remember, we have a radical in the denominator and we also have addition. When there's addition in the denominator, we have to, in order to get the radical out or to rationalize our denominator, we multiply by the conjugate of the denominator. Root 2 minus 7, the conjugate is root 2 plus 7. Now on top, we're going to multiply by root 2 plus 7. Same thing. Now, we have conjugates, or we say that these are real conjugates. Root 2, here, let's go and write it. Root 2 minus 7 times root 2 plus 7. Remember that real conjugates, real means there is no I. There is no imaginary unit. Since these are real conjugates, they do not have an I, we can use the trick. Root 2 times root 2, multiply these together. Root 2 times root 2 is 2. Now, multiply the 7 times the 7. 7 times 7 is 49. And since these are real conjugates, what does this produce? This produces a difference of squares, or just subtraction. So 2 minus 49 gives a denominator of negative 47. So we have negative 47 in our denominator, and on top, multiplication of a monomial. Monomial, multiplication means addition. We distribute. 5 times root 2 is 5 root 2. 5 times 7 is 35. We generally like to put the number first, 35 first, and the radical second. So apply 5 root 2 second, all over negative 47. Remember, when there's a monomial in the denominator, you have to split the addition in the numerator. So we're going to write this as 35 over negative 47, and we're going to let the negative float to the top. or out front, either or. So we're not going to put the negative in the denominator and let the negative float to the top. This is negative 35 over 47, and we have plus 5 root 2 over negative 47, and in this case the negative is going to float out front, and we're going to have plus negative 5 root 2, and the plus negative will change just to subtraction. So let's see that again. If you have addition and a negative down below, the negative can come out front, change the addition to subtraction. So we're going to take the negative out of the bottom and change this to minus 5 root 2 over 47. Question, does anything divide 35 and 47? No. Does anything divide the 5 and the 47? No. Then we are done. This is our final answer. One more. If you're looking at 7 plus root 2 over root 3 minus, say, 11. In this case, well, let's do 11 minus root 3, or 11 plus root 3. 11 plus root 3. Okay, if there is a radical in the denominator and there's addition, we multiply by the conjugate of the denominator. So we're going to multiply by 11 minus root 3 and 11 minus root 3. Now the bottom, we can use our trick. Since these are conjugates in the denominator, we can remember, since there's also no I, these are real conjugates, and real conjugates produce a difference of 2 perfect squares. So we can simply just square the 11 and square the root 3. What is 11 times 11? 11 times 11 is 121. And what is root 3 times root 3? Hopefully you say at this point, root 2 times root 2 is 2. Root 7 times root 7 is 7. Root 3 times root 3 is 3. Now, remember that real conjugates produce a difference or subtraction of 2 perfect squares. So we're going to put subtraction between this. 121 minus 3 is 118. Now on top, we have a binomial times a binomial we have to FOIL. Take the 7 times the 11, this is 77. 7 times the root 3 is, well, 7 times negative root 3, we glue it together, putting the 7 out front. This is minus 7 root 3. And over here we take the root 2 times both. So root 2 times 11, put the 11 first. This is 11 root 3. And then the root 2 times the root 3, we multiply the radicands together because the 2 and the 3 are both underneath the root. Positive times negative is negative. Root 2 times root 3 is root of 6. Now, one more step. Since we have a monomial in the denominator, we split the addition. So this is 77 over 118. And this is negative 7 root 3. Go ahead and put the negative out front. The negative becomes a subtraction. Negative 7 root 3 over 118. And let's see, plus 11 root 3 over 118, and minus root 6 over 118. And question, does anything in 77 cancel with 118? No, it does not. 77 is 7 times 11. 118 is 2 times 59, and 59 is prime. So we have nothing here cancels. 2 and 59, nothing in 2 and 59 cancel with 7 and 11. And same thing with the next. 7 does not cancel with 118. 11 does not cancel with 118. This is your final answer. And reminding you, we are simplifying. Does simplify mean to make simple? No, it does not. Notice what we started with. We started with a problem that looked fairly simple, and we ended with something that looked very ugly. So simplify does not mean to make simple. Simplify means to add, subtract, multiply, and divide till you cannot do this anymore. Also, follow rules of no negative exponents in the final answer and no radicals in the final answer. So we have to follow these rules, and our final answer is much, I would say, in my opinion, much uglier than what we started with. So again, simplify does not mean to make simple. Most of the time, what you get as an answer does look more simple than what you started with, but not always. Now, let's see. Almost ran out of space there in the end. Try to keep these lines to know where the edge of the camera is. So now we're going to look at complex conjugates. How to use this trick with respect to complex conjugates? Well, if you're looking at, say, 5 plus 2i over 4 minus 7i. Okay, so in this case, we have to divide two complex numbers. Remember, to divide complex numbers, same thing. We multiply by the conjugate of the denominator. 4 minus 7i, the conjugate is 4 plus 7i. We change the middle sign. If we multiply the bottom by 4 plus 7i, we multiply the top. Now on the bottom, we can use the trick. Since these are conjugates, we can remember that product of complex conjugates, complex because there's an I, complex conjugates produce a sum or addition of two perfect squares. So we can simply square the 4. 4 times 4 is 16. And square the 7. 7 times 7 is 49. And since these are complex conjugates, they produce a sum of squares. We put addition. And 16 plus 49 is 65. So we end up with a denominator of 65, and on top we FOIL. 5 times 4 is 20. 5 times 7i is 35i. 2i times 4 is 8i. And 2i times 7i is 14i squared. Now, we have I squared on the end. Remember, I squared changes to negative 1. Or negative 1 times 14. This changes the 14 to negative 14. 20 minus 14 gives 6. 35i plus 8i is 41i. And this is all over 65. Now, what am I doing? 35 plus 8 is 43i. I make these mistakes. I'm not thinking. Okay, so 35 plus 8 is 43i. 20 minus 14 is 6. Now, since there's a monomial in the denominator, we split the addition. This is 6 over 65 plus 43i over 65. And does anything in 6 cancel with 65? No, it does not. So our final answer is 6 over 65 plus, and you can write this as 43 over 65 with parentheses around the fraction and an I out front. Do you see a real part and an imaginary part? Yes, you do. A complex number, or I should say the division of two complex numbers, doesn't result in a complex number with a real and an imaginary part. Yes, it does. Now, one more. If we say 7 plus 2i over 1 minus I, you just have to be a little careful here. Notice we have 1 minus I in the denominator. We multiply by the conjugate of 1 minus I, which is 1 plus I. And on top, we multiply by 1 plus I. Now, on the bottom, we can use a trick. Square the 1. Since these are complex conjugates, they produce a sum of squares. So put addition down here. 1 times 1 is 1. And what's in front of the I? Well, there's a 1 in front of the I. 1 times 1 is also 1. So we end up with 1 plus 1, which is 2. Our denominator is 2. Now take the 7 times the 1 is 7. 7 times the I is 7i. 2i times the 1 is 2i. And 2i times the I is 2i squared. Now remember, the I squared is going to change the 2 back to negative 2 because I squared is negative 1. We end up with 7 minus 2, which is 5. And 7i plus 2i is 9i, all this over 2. Since we have a monomial in the denominator, we split the addition, write the final answer is 5 over 2 plus 9i over 2. Or we can write this as 5 over 2 plus 9 over 2 in parentheses I. Either form I will accept, but I want you guys to see that a complex number has what? A real part and an imaginary part. Does the division of two complex numbers result in a complex number? Yes. This lesson, the primary, most important thing you need to know from this lesson is that a product of real conjugates produces a difference of two perfect squares, and a product of complex conjugates produces a sum of two perfect squares, and we're going to label this in the future. So we're going to see x plus 5 times x minus 5. We are going to call this a product of real conjugates, P-O-R-C. Students sometimes say pork. That's one way to remember it. Okay, so now we're going to FOIL, or instead of foiling, we're going to use our trick. Since these are real conjugates, there's no I. We square the x, which is x squared, square the 5. 5 times 5 is 25. These are real conjugates, so we put subtraction between this, and we call the answer a difference of squares, DOS. DOS. I think of this as an old computer program. Now, operating system, I should say, old computer operating system. So now we have, in this case, x plus 5i multiplied by x minus 5i. Here we see an I on the end. We call these complex conjugates. We can simply use our trick. Complex conjugates result in a sum of two perfect squares. We're going to label this product of complex conjugates, POC. P-O-C-C. Product of complex conjugates results in a sum of squares, SOS. I think of, I need help. Okay, I don't know if you guys know the old SOS. The dash, 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 anyway, Morse code. So we FOIL, or we use our trick. X times x gives what? X squared. 5 times 5 gives 25. Since these are complex conjugates, this results in a sum of two squares, or x squared plus 25. This is our final answer. This is our final answer. And good luck on your homework. Take care. See you in the next video.